In this video, we're going to look at just the basic graphs of sine and cosine. And when I say basic, we're not going to delve into all the little intricate details with all the transformations. We're just going to look at some basics. So you can see in front of you that sine and cosine have the same basic structure when it comes to their equations. You can see that you have an A for the amplitude, you have K, which is your wave number, and that has to do with the period, and we'll see how to determine the period here in a little bit using K. Then you have B, which is your shift left and right, and then you have your C, which is your shift up and down. So these are very similar to what you saw when you were doing transformations of other types of functions. And we're just going to look at these, and I'm actually going to give you some pictures and some visuals on graphs so that you can actually see how these waves move. Now, we did a lab in our class on harmonics, or a little bit, and we talked about the sine wave as it applies to music. And so if you're not familiar with that, in when you hear sounds, you have this formula right here. And what this formula is this tells you the sine wave for different types of sounds and pitches. Now, the P, that represents the pitch. And when that represents, meaning that it represents the number of hertz that are present with that particular tone. Now, hertz are measured in how many vibrations per second. The human ear can hear up to, I believe, 20,000 hertz per second, or 20,000 hertz. And of course, that's if you have a perfect ear. There's a lot of places you can go online and make yourself upset by realizing how much hearing you've lost over your lifetime. But there are a lot of different hearing tests you can take. And as you get older, you can hear fewer pitches. A lot of times you can't hear pitches that are out of a higher vibration level. So, anyway, the P is the pitch, the M is the volume, and usually that's measured in decibels. And this is not a perfect representation of a sine wave because you can have different instruments, for example, a flute, a violin playing the same note. And even though they're at the same volume and playing the same pitch, they may not have the same wave because there's a lot of things that affect it. Comes into, air pressure and other variables that affect it. But anyway, this is your base equation. So what we talked about, going back to this, is that A, the volume is the amplitude if you're looking at sound, and the K is going to be your frequency when you're looking at the sound. So let's go to a calculator. Okay, so right here you see a sine wave. This is your basic sine x. And when I say your basic sine x, I can actually go back and do this. Bear with me. This is the same thing as writing this. This is, if I can get it to work, there we go. F of x equals 1 sine x. So, whoops. So 1 sine of 1 times x minus 0 plus 0. And I can't get all of this on the screen, so let's try this one more time. So you have f of x equals 1 sine of 1 x minus 0 plus 0. And if you go back and you look at the actual equation itself, you'll see that we have an amplitude of 1, a periodic factor of 1. We have no shifting left or right and no shifting up and down. This is almost, I guess, what you would call the parent sine function when we refer to families of functions. So I'm going to erase this. I'm going to go back to the notes screen. And when I go back to the notes, you can see the amplitude on that particular one was 1. A was 1, K was 1, B was 0, C was 0. That's your parent sine function. Same thing holds true for cosine. So let's go back to the calculator. So I've got an amplitude of 1. I have a period of 2 pi, because remember, the period of a sine function is 2 pi. If you look at the graph, you can actually see, and let me go ahead and pull up my pen here, my pen tool. You can actually see that sine starts at 0, it goes up to 1. And remember, the range of a sine function and a cosine function is always from -1 to 1 when you're looking at basic trig and you're not looking at any factor change or amplitude changes. It goes up to 1, comes back down through 0, goes to -1, and comes back to 0. That is one period, and that's 2 pi. That's how long it takes for the sine wave to start its journey and go all the way through until it gets back to where it started and repeats its cycle. This period is also called the wavelength. And when we look at pitch and sound, the higher the pitch, the shorter the wavelength because the faster the vibrations. So you can see that the wavelength here is just 2 pi because we're doing a simple 1 sine of x. Now let's start changing some of these variables here. So I'm going to take this equation, I'm going to take this and put it down here. So I've got sine x. Now I'm going to go back into my graph and I'm going to go up to the top and I'm going to graph sine of 2x. Now what that means is, if you remember, if I go back here, now that means that I'm looking at this right here. I'm looking at the period factor. So I'm going to do 2x and I'm going to graph this, and I want you to see what happens to the wavelength. Now look at the difference between the blue and the red. The red, you can see, still has a wavelength of 2 pi. It goes from 0 up to the top, back to up to 1, back to 0, down to -1, and back to 0. And again, that is at 2 pi. If you actually want to see what these are, you can do a graph trace. So if I go, I'm on the blue one right now. Let me get, there we go. I'm on the red. There's my maximum. I'm going to hit my 0. I'm going to go down. Where's my minimum? You notice at -1. And then I'm back to 0. Now look at the x coordinate here, 6.28. That's 2 pi. That's 2 times 3.14. So the red one is the one where we had 1 sine x, right? Sine of 1x. So it has a regular period. Now let's jump to blue. I'm going to go back to the beginning. So I'm jumping to blue now. Blue starts at 0, goes up to 1. That's its max. Goes back through 0, down to -1, and back up to 0. What do you notice about the x coordinate here? It's 3.14. That's pi, not 2 pi. So by doubling the coefficient of my angle, of my argument here, I cut the period in half. So basically what you do when you're trying to find the period of a function, of a sine function, the period itself, and I'll write this off to the side, to find the period, you actually do 2 pi divided by your k value. So in the last example, so 2 pi, get that in your brain, 2 pi divided by k. In this last function, I had sine of 2x. So I can actually go to my pen tool here. If I have sine of 2x, that means my period is going to be 2 pi divided by that 2, which gives me a period of pi, which is why we have this number. The regular one, I'm going to go back to the other screen. If I jump functions again, if it's going to let me, go back to the mouse. Click back here. It's going to let me jump functions again. If I look here, now I'm at 6.28, which is 2 pi. 2 pi divided by 1, which is 2 pi. That's why it has a different period. So you can see that the bigger this number gets, the quicker the wave cycles. And that's how that number affects. We're not going to look at all the shifting left and right today or the up and down. We're just looking at how the period is affected and how the amplitude is affected. Okay, so I'm going to get out of the trace tool and you can see my two functions. Now I'm going to go back to a simple function and we're going to look at amplitude. So I'm going to go back, if just for fun too, if you want to see what happens for x, that one is an even shorter period. That would be 2 pi over 4, which means your period would be pi over 2. So let's go back and let's take all of these out and let's look at our basic parent sine wave right here. F of x equals sine of x. Now I want to alter not the pitch, which is what we altered earlier, but I want to alter the volume. So let's look at the volume. That's amplitude. That's the capital A. Now notice with the capital A, I'm going to go in and instead of this being 1 sine of x, I'm going to go and I'm going to take one of these other functions and I'm going to change this function. We don't want to change the period now. We want to change the amplitude. So I'm going to change the function to 2 sine x. Now you'll notice that you can't see the other function, and I think that's because there might be an error or it didn't save. Okay, so I didn't select it. Now watch when I select it. All right, you got something that's literally off the charts. So let's go to Menu, Windows Zoom, and Zoom Fit. All right, now let's take a look at amplitude. So if I hit Graph Trace, look what happened when I put a 2 in front of my sine wave. My original sine wave is the red. So once again, I'm going up to 1. And you can already see that's going to be a major difference between the two waves. I'm going down to 0, down to -1, and back to 0. And you can see 6.28. That is a period of 2 pi. Now let's examine the blue. I'm going to go all the way back to the beginning for the blue. If the blue goes up, back down, all the way back up, but guess what? The blue also has a period of 6.28, which is 2 pi. When you change the amplitude, it does not change the period of the function. The wavelengths are the same. The cycle is the same. The amplitude is your vertical stretch. The period is your horizontal stretch, which we saw a while ago. So when you look at the two equations, let's go back to my functions. I have 1 times sine of x, which is the red one. And I have 2 times sine of x, apologies for the yawning, which is the blue one. And you noticed what's happened is it's literally the amplitude has doubled what we call the crest. The crest is higher. So when you look at the waves, this one's twice as tall. And if you go to trace, what you'll see on the blue one is everywhere the red one was -1, now the blue one is -2. It doubled. Everywhere the red wave was 1, it is now 2. It doubled. So if I wanted to do one more, I'm going to enter one more graph, and I'm going to go up here to this guy, and I'm not going to make this 4x. I'm going to change this to 0.5 sine x, and I'm going to put it in, and I'm going to graph it. I'm going to select it. I should have selected it. Now look what happens. I've done 0.5, so it should be half of the red. And if you notice, when you do trace and you do the graph trace, I'm going to jump down to the red one. The red one, when the red one is at 1, the blue one is at 2, the black one is at a half. But once again, what is the period for the black one? Exactly the same, 2 pi. So basically, what you need to know for our purposes, we're not going to do any shifting for right now, left and right or up and down, but you need to know how the amplitude affects the wave and how the period factor affects the wave. The period factor is usually going to be like when you're doing sound, it'll be your hertz, your pitch, but you have to look at those two specifically. The A and the K are your vertical stretch and your horizontal stretch. And that's all we're looking at on our test for sine and cosine.